Welcome to Forth and Beyond. My name is Timothy Lottis, and this is the Neo Kino Graphics channel. This talk will not be covering standard Forth. Instead, this talk is going to start with the Beyond Forth part. Let's begin. What if we didn't actually need Visual Studio? What if we didn't need a separate debugger, or even to see language? Let's start with the first principle. Question everything until the problem is truly minimized. Begin by peeling the onion of computing, passing through APIs, compilers, languages, code generation, and so on. Search the alternative realities until greatness is found. And we'll start by rewinding time and learning from the past masters. We'll start with the most basic interactive computer tool, the calculator. My favorite calculator was the HP48. That's what I used. HP48 used reverse Polish notation. This made it very easy to type in math and get answers. You didn't have to mess with parentheses. The HP48 provided RPL. The later machines provided system RPL, which could even assemble machine code. With offline tools for the HP48, people even built games for these machines. Now what if we were to take that calculator and evolve it to something more Forth-like? We'll start with simple reverse Polish notation calculator math. And next we'll introduce a dictionary. The dictionary will point to positions on the data stack. For instance, in the second line here, we have a red word, 4K. That 4K word would be pointing to the next stack item. Next stack item, we can do some evaluations to come up with the number 4. So we type in 1024, then type in 4, and then type in multiply. And now we have 4096. So the 4K word would point to 4096. This is a basic way of doing a variable. The next thing we could do is we could actually build numbers which represent opcodes, or multiple numbers which represent opcodes, things that we could actually execute and have do an operation on the machine. So in this case, there's drop, and drop points to a number on the data stack, which disassembles to add ESI, -4, and then returns. Drop would basically drop the top item from the data stack, where ESI is pointing to the data stack. And now, once we have this in our dictionary, we can continue to do things on the stack, and we can use drop if we want to. So now we could write 4K, which would pull that number 4096 that we had put in the dictionary prior, and then do 1, and then do 2, and then a plus, which will create a 3, and then we execute drop, which will drop the 3, leaving 4096 on the stack. And thus now we've created something quite powerful. So in this context, the gold numbers get pushed on the stack. The gold words get its value in the dictionary pushed on the stack. The green words are getting a value in the dictionary executed, and the red word is putting a pointer to the top of stack in the actual word in the dictionary. In some respects, you can see how this starts to create an extremely powerful system. So a Forth-like machine is really the ultimate form of tool building. The language is freeform. The dictionary defines words. These words become the language you program in. It enables any kind of factoring of a problem. The language, the assembler, the compiler, the linker, the editor, the debugger, they're all defined in the source itself, and these systems can be tiny. Tiny as in the whole thing fits in the cache. In my opinion, a Forth-like machine would have been a better option than BASIC for a boot language. A lot of people learned BASIC because they could type in a program from a book, say on the C64. But imagine if it was a Forth machine instead. You have something that runs significantly faster and is significantly more powerful. The irony here is later, Apple, IBM, and Sun, they actually used a Forth-based open firmware, but few had programmed in it at the time. So let's look back at Forth. Forth was invented in 1986 by Chuck Moore, or Charles Moore. Chuck later focused on building multiple stack-based processors. He used his own VLSI CAD system, OCAD, for layout and simulation, and these were written in his language. Early, it was a sourceless language, and later it got moved to ColorForth, from my understanding. The images below show some of the actual editor and simulation. These are from the Ultra Technology site. What's impressive here is that these were dramatically small systems, and yet they were used to do some of the most complicated stuff that humans can do, which is design chips that actually got fabricated and got used. Chuck Moore's ColorForth, I think, is worth learning about. It's an example of real system minimization. 32-bit reverse Polish notation language. It provides a data stack, which gives you memory to work with. And note, code is compiled onto the data stack too. It provides dictionaries, which map a name to a value. The value is typically a 32-bit number or a 32-bit address to the source or data stack. The dictionaries are searched in a linear order from last to first defined word. There are two main dictionaries, the Forth one, which is used for words to call, and macro, which is a secondary dictionary used for words that do code generation. Source is broken up into blocks. There is no file system. Inside the source blocks are 32-bit tokens. These tokens contain 28 bits of compressed name or string and 4 bits of tag. The tag controls how to interpret the source token. Let's go through some of the tags. The white tag means an ignored word. Yellow tag means execute. If it's a number, we append the number on the data stack. If it's a word, we look up the word in the dictionary and then we call the word. If it's a red word, we're doing a definition. We're setting the word in the dictionary to the top of the stack, or a pointer to the top of the stack. If it's green, we're compiling. If it's a green number, we're appending a push number onto the stack. Effectively, we're encoding the code, the machine language that would push that number. If we compile a word, if we're in the macro dictionary, we're first going to look up the word in the macro dictionary, and if it exists, we're going to call it. Otherwise, we look up the word in the fourth dictionary, and we append a call to the word itself. Cyan, or blue, is used to defer words, execution. So we'll look up the word in the macro dictionary, and we will append a call to the word. This way we can make words that do code generation, that call other words that do code generation. Next is the variable. Variable is used by magenta. Variable sets the dictionary value to the word to the pointer to the next source token in the source code as it's being evaluated. And then anytime we have a yellow to green transition, we pop a number off the stack and then we append a push number to the data stack, which basically means we're taking a number and we're turning it back into a program that pushes the number. So if we look at some of the blocks inside ColorForth, notice this one here, block 18, this starts doing the code generation. So it'll push 24 and then it'll load, which will take block 24 and actually bring in all the code generation macros. And then the next one, 26 load, will bring in more code generation macros from block 26. If you look at block 24, it starts with executing macro, which moves us to making defines in the macro dictionary. The first define is swap, then it does 168b, and then it does a 2 comma. The 2 comma pushes 2 bytes onto the data stack. The next one is C2 8b0689, followed by a comma. The comma pushes 4 bytes onto the data stack. So effectively what we're doing is we're pushing some bytes to actually create code onto the data stack where swap is defined. And if we disassemble these 6 bytes, we get move edx, comma, dword ptr esi. So effectively, we're pulling from the stack into edx. And the stack in this case is the data stack of fourth. The next one is move dword ptr esi, comma, eax. So we're pushing the existing cached value of the top of the stack, which is in eax. We're putting that on the stack. And then we move edx into eax, which is taking the old second value on the stack and pushing it into the cached value, which is the top of the stack in ColorForth. So basically this whole block is defining opcodes that are used for code generation. So let's fast way forward now, and let's just critique ColorForth. Perhaps one of the biggest critiques of ColorForth is that it's a mismatch to hardware today. It's a stack-based machine, and modern machines are register-based. Modern machines have really deep pipelines, they don't deal with branching well, and Forth is extremely branch-friendly. The interpreter costs that you have to do per token are pretty high. We have to branch based on tag. Dictionaries are searched from last added to first added with no hashing or any acceleration. Most commonly, every time you do an interpreting after branching on the tag, you're going to branch again to another thing, which is going to be a mispredicted address. And note, you got an average of 16 clocks stall on, say, Zen 2 for a branch misprediction. Of course, the logical response here is if you only have a tiny amount of code, there's no reason it has to be super fast. After all, the most important optimization is doing less total work. For example, an F1 car driving 1,000 miles is going to be substantially slower than a turtle walking 1 foot. Well, towards the end of 2025, Chuck Moore said, "I think fate is trying to tell me it's time to move on." And this is in response to Windows auto-updating and then breaking his ColorForth. But I ask, should we actually move on? The world did move on to mass hardware and software complexity, but perhaps Chuck's way of thinking is actually exactly what is needed today. How about a localized reboot? We have a lot of FPGA-based systems showing up, and I'm hopeful that they're getting commercial success. But these are effectively all emulators of prior hardware. What about doing something new? Maybe forth thinking could be a part of that. What about neo-vintage parallel machines? After all, forth thinking is ideal for a fixed hardware platform. FPGA-based hardware emulators focus mostly on the serial thinking era, but this is actually a universal speed of light barrier. These product lines are going to stop around N64 and so on, because after that, serial CPU clock rates cannot be FPGA emulated. But FPGAs have crazy parallel DSP capabilities. Perhaps we should design for DSPs as the processors, and then provide radically parallel, but medium clock machines. And these are things we could actually drive with the Forth style language. There is a challenge of minimalism in a maximalism world. Software is a problem, but the root is hardware complexity growth. For example, our DNA4 ISA guide is almost 4 megabytes in itself, and try writing a modern USB-C controller driver yourself. And yet, even with all of today's hardware complexity, I still believe Forth-inspired software can be quite useful. I spent a lot of time exploring the permutation space around Forth, specifically more around ColorForth, and seeing what variations could be made. One way I varied from Forth was in an opt encoding. I don't necessarily stick with a stack-based language. Sometimes I treat the register file more like a closer, highly aliased memory. Sometimes use a stack-based language, however, as a macro language, say for a native hardware assembler. And sometimes I mix a stack-based language with something that has arguments. For instance, having a word have arguments after the word and still use it like a stack-based language. So I have used Forth-like things in commercial products. One example is I used to run a photography business and a software development business. And the old business website that I ran in my prior life, doing landscape photography, was actually generated by a Forth-like language running server-side, which generated all the HTML pages. It made managing a huge website actually practical. Now I had to use the Wayback Machine to find this, so sorry in advance for the broken images. And of course I had a different last name then from a broken marriage, but that's another story. But I did a lot more Forth-like things beyond this one. One of the things that got me right away was, of course, the lure to optimize. For example, ColorForth uses this Huffman-style encoding for its names and its tokens. Remember, a source token is a T-bit tag, typically T is 4, with an S-bit string, where S is 28 bits. We could do a better job of encoding the 28 bits. For instance, we could split that full number range by some initial probability table of the first character. And then we could split each of those ranges by, say, a 1 or 2 character predictor. And then we train this thing on a giant dictionary. And of course, you're going to have to use lookup tables. And of course, the memory used for the predictor is going to be greater than the rest of this whole system combined. And yeah, it worked. It provided some very interesting stuff. You could put a number in and it would basically BS you a string out, which was pretty cool. This journey I think was useful. I learned a lot of things in the process, like where to optimize and where not to optimize. Next question is, well, should we hash or should we not hash? It turns out that a compressed string, like in the prior slide, is actually a great hash function. I can simply mask off some number of the least significant bits, and that becomes my hash function. Or for hashing, I always dislike the issue of only part using cache lines. That's not very efficient. And of course, we can try to fix that too. We can check a very tiny hash table first and size that hash table to stay in the cache. And then if we miss on that, we can go to the full size one, the one that's going to have pretty poor utilization on cache lines. And assuming lots of reuse, that tiny hash table is going to keep high cache utilization. However, now we've done 2 stages of optimization, but we really should start asking, why are we hashing and why are we compressing? Why are we doing all this overhead? Why do we just not direct map? After all, if we're depending on an editor, we could just direct map. Or perhaps just address into the dictionary directly. And we can split off the T-bit tag and the S-bit string for editor use. And that can start simplifying things so we don't have all this complexity in the first place. The next thing we can do if we're interpreting is we can solve the problem of branch misses. Normally with an interpreter, you would evaluate the word and then you'd return back to the interpreter. That interpreter would look up another word and do another branch, but that branch would always be mispredicted. One option is we could just fold the interpreter back into the words themselves. But of course, we've got to make that interpreter really small, otherwise we're doing a lot of code duplication. You can imagine if you have 1,000 words, you're going to embed the interpreter 1,000 times. So there's a lot of different ways we can design an interpreter down into a few bytes. For instance, this one is a 8-byte interpreter. This is one I've never used. Actually can do better than 8 bytes, and I'll show you that towards the end. So of course the best way to learn is to build stuff. so I built many ColorForth inspired things over the years. Some, like the one to the right here, I got distracted with editor graphics, effectively making something extremely nice to use and very pretty. This one was cool. The dictionary I moved into the source itself, and I did a direct binary editor. So this thing, you'd actually see the cache lines, and you're effectively doing a hex editor that uses tags to tell you some contextual information. And then each line, of course, has a comment on the top followed by the data on the bottom. And of course, I use different fonts because sometimes I'm packing a full number with, sometimes I'm packing characters and so on in comments. It was a relatively complicated system, but actually simple when you think about it in the context of what we build today. One of the first questions to ask yourself is whether you want to work with text source versus a binary editor. So sometimes I would work with text source. In order to make this work well, I would have a prefix character in front of every word, which basically would be the tag. And it would also enable me to use very simple syntax coloring inside, say, Nano. Most of these I built, they were more like a fourth macro language that was used to create a binary. So what I would do, and for instance, what you can see on the right, is I would define something that would enable me to build the elf header. And then after the elf header was built, I would actually write the assembler in the source code and then finish off the rest of the binary. These kind of languages are extremely small, and the whole thing is in, say, a few kilobyte binary. The other thing I do with these is I bootstrap. So the first time I might write the thing in C, and then C would evaluate, and then I'd run the interpreter in C, and then later I would rewrite the interpreter inside the source code and then compile that. Now I would be bootstrapped into the language itself. And so by doing that, I could actually compare my C code to the code I wrote inside my own language. And of course, I'm faster inside my own language than in the C code. And of course, I'm a lot smaller in the binary as well, because I have a very, very small elf header in the binary that I generated compared to the one that, say, GCC would generate. I built some custom x86 operating systems. It was fun to build custom VGA fonts and, of course, mess with the palette entries to improve the initial colors. And I did lots of different fourth variations, but typically these projects just got blocked in the mass complexity of today's hardware, meaning once you get down to the point where you want to, say, draw something on the screen other than using, say, the old DOS VGA frame buffer, or if you want to start using input, you start needing a USB driver, and then all of a sudden everything turns into a nightmare. One thing I mentioned before is it's very nice to use a fourth-like language as a macro assembly language. Traditional assembly language, you do something like, say, add ECX, EDX, and then colon advanced pointer by stride. The later part here is heavily commented. In fact, typically assembly is mostly comments. Otherwise, a human can't really understand it. When you start using a fourth-like language as a macro assembler, a lot of times what you do is instead of using the register number, you would just put the register number inside another word and then use that word. So now you start self-documenting. And if you had common blocks of, say, multiple instructions, you would start defining those in some other word, and then you start factoring. And this way you self-document everything, and it becomes actually very easy to understand. A lot more easy to understand than, say, assembler. And on top of this, of course, you can also put comments, but you don't typically need as many. So if we were to look back at some of the lessons of all these projects, I think the key thing is that when your OS is an editor, is a hypercalculator, is a debugger, is a hex editor, you end up with this interactive, instant iteration software development. And that part is wonderful. The fourth style of thinking keeps source small enough so that it's approachable by a single developer. And that, I think, is very important. You basically build out your own tools for exactly the way you like to think. And that's where its true beauty lies. Others like Onat have built full systems, meaning he is running something that actually works with Vulkan and generates SpearV. So there is another option, and that is going sourceless. No language, no assembler, the code is the data, or the data is the code. Chuck's OK was a source of inspiration. I've only read about this, but it did send me down a spiral of trying various ideas that are related to what I read. So when we think about sourceless programming, it's best to just work from the opposite extreme. Start with, say, a hex editor, and then work towards what we would need to make that practical for code generation. So I think of a binary as an array of, say, n 32-bit words. And then we could have another thing, which is an annotation, which is an array of n 64-bit words. The annotation could provide a tag, which gives context to the data, or could control how the editor manipulates the data. The annotation could also provide an 8-character text annotation for the individual binary words, which serves as documentation for what the word is for. So part of sourceless programming is how do you generate code? And with Forth, hand assembling words is actually relatively easy because you don't have that many low-level operations if you're doing a stack-based machine. I invented something called x68, which I'm planning to do a separate talk on. It's a subset of x64, which works with opcodes at 32-bit granularity only. Note that x86-64 supports ignored prefixes, which can pad opcodes out to 32-bit. And we also have multi-byte no-ops, which can align the ends too. And we can do things like adding in rex prefixes when we don't need it to, again, pad out to 32-bit. So for instance, if we wanted to do a 32-bit instruction for return, we might put the return, which is a C3, and then pad the rest of it with a 3-byte no-op. And once we've built this 32-bit return number, which we can annotate with RET, we can insert a return anywhere just by copying and inserting this word in the source code. And later, if we build different opcodes and say they were multi-word, we can just use find and replace to change those. Effectively, we're moving compilation into some edit time operations. One of the nice things about being at 32-bit granularity for the instruction is that the 32-bit immediates are now at 32-bit granularity as well. And so now we can just make it so that we have a tag which says this is an opcode and a tag which says this is, say, an immediate hex value, and we could show them separately with different colors. In this case, I have code for setting ESI to a 32-bit immediate, and you'll notice that this one is using the 3E ignored DS segment selector prefix to pad out the opcode to 32-bit. And then after that, we have a silly number which we're setting into ESI. That silly number is 1, 2, 3, 4, 5, 6, 7, 8 in hex. So it's very easy to do inline data this way. Of course, calls and jumps are another question, and we have an easy solution for that one as well. In x86-64, call and jump uses a 32-bit relative immediate, and that relative is relative to the end of the opcode, not the beginning. And so if we want to make an editor support this, we would just tag the relative branch address as a word that is a relative address. And then when we start editing text, or say editing the words inside the binary, and say we move things around, we would just relink all of the words in the binary that have a relative address. So as code changes, things just get fixed up. And so this effectively solves the call and the jump problem. It's very easy to make an editor which repatches everything. Conditional branches, you might think those are complicated, but they're actually not. Conditional branches is just an 8-bit relative branch address. And so when I make words on these, I would say jump on equal -2, which would jump on equal to the word that is 2 words before this one. Or say JE -4 for 4 words minus, and so on. And so I can just build a few of these constructs and change the opcodes around whenever I need, say, a jump on 0 or so on. Nice thing about this is now you no longer have to label things because you just go and count. And when you move it around, it's all relative, so you don't need to do any patching. If you want to add more stuff in your loop, you just change, the opcode a little. Another option is the editor could have a built-in 32-bit word assembly disassembly, meaning I could use a shorthand for registers and opcodes. And the shorthand that I would use would be labeling the registers starting with G, so that 0 through F could be used for hex. So this is an example of how you might want to do it. So in this case, I have H plus at I08, which is going to disassemble to add RCX quad word pointer RDX plus 0x8, which we can shorthand very easily. And so I could have an editor that would show you either the disassembly or show the shorthand instruction for it. And that would aid in the understanding and ability to insert stuff without using separate tools. So I did build this sourceless system once in the real. It was back when I was building tiny x86-based operating systems. I built the editor as a console program. So this would run in Linux. And I would build binaries in that console program. And then I would use an x86 emulator running in Linux to actually test them. And this was a pretty liberating experience. I learned a lot from there. On the right, I'm showing one of the boot sectors of one of the examples running in the editor. Note with sourceless programming, we could extend the annotation quite a bit. For instance, we could have tables that map register numbers to strings, and then for each cache line, we could have an index of a table. In this way, registers could be automatically annotated. For instance, if register 2 is set to position and register 4 is set to velocity, if we had add R2, R4, we could just put in add POS, velocity, right? And that would make it a lot easier to understand automatically. We could also extend and have each cache line have a string as well. In this way, we could automatically annotate, say, a label. The first word maybe could be the label, and the rest of the string could be used for a comment. So there's a lot of ways to do sourceless programming where we just provide annotation tools to actually make it a practical experience. So let's talk about some of the variations, the pros and cons. The easiest way to perhaps start this would be to work with text source. And usually with text source, you're going to use prefix words for the tag, for instance, slash for comment, colon for define, maybe tick for execute. This does have the slowest runtime, however, because you have a character granularity loop. It does have a benefit in that for you to get started, there is no editor that you have to write. You can use an external text editor, and you can do easy custom syntax coloring. It's going to be very easy to understand and to work in. However, I think you're missing a big piece if you go down this path, and that is you don't get any live interaction or debugging. You're basically depending on the fast compile times of your custom language and the fast load times of whatever program you're doing to try to get you in that iteration loop. And you can work this way. I've done it many times. But the experience is nowhere near as good as doing the full interactive one with a binary editor. I guess one of the other benefits here is you got very easy code portability. There's no binary files, just text files. You can copy and paste as you will. Of course, the next jump up from that is going to binary source. This would be middle performance runtime because now you're working at a word granularity inside your interpreter. You have portability because you have code generation that can adapt to the system. Meaning as you interpret your code, you can look at what's underlying in the hardware and you can make changes to how the code is generated at runtime. You can build just what bits of an assembler are needed. You don't need to build out everything like you would with, say, a disassembler tool or an assembler tool. So for instance, with x86, I don't actually generate much of the ICE. I only use a very, very tiny subset. You do have to write the binary editor, and that can be a lot of work, and sometimes that presents a problem with bootstrapping because you don't have the language to write the editor in from the beginning, so you have to write the editor in some other language, and then in that language, write the editor again, and then, complete the bootstrapping process. The one benefit here is you get interactive development and debug from the beginning. And also, now your source code shows how constructs are built, instead of just showing the result as you would get with, say, source-free. One interesting thing about Forth with binary source, and this concept that you can rebuild source code at runtime at any point in execution, is now you can start compiling things you load into machine code, and then you don't have to run all the overhead. Basically, you can bake things into machine code anytime and edit time. And that's a very powerful feature. Now, if we go and look at sourceless programming, there's a bunch of pros and cons. The one pro is that it's the fastest runtime. It's a true no-op. You can build things that are highly, tightly optimized for a platform, and they're as optimized as you could possibly get. You do, however, lose capacity for showing how constants came to be, and you lose the capability of adapting to what the machine is. You can work around this, however. You can make smaller embedded constants that you write into modified bit fields and instructions, but it's really taking a little too far in terms of complexity. You do need to write an editor, which includes an opcode assembler and disassembler potentially if you want to go down that route. And if you're going to do CPU and GPU, that's a lot of work. It can be very complicated when systems include auto annotation. For instance, if you want to type in, say, a string readable register and then have it go and figure out what register number that is. I guess the primary disadvantage here is that there's no possibility for portability. You have a raw binary editor. And today we have a problem with GPUs. Steam Deck is RDNA 2, Steam Machine's RDNA 3, and who knows, the future may be RDNA 4 or 5 or 6. The problem with this is that when the ISA changes across those chipsets, that can result in different instruction sizing. So you can't just do simple source free. For example, MIMG in RDNA2 has a different size than VImage in RDNA4, and that's all due to the ISA changes. So if you do sourceful programming, you can port through a compile step. However, sourceless, you would need to do something else, and perhaps that is just rewriting chipset-specific versions of all the shaders, but that may be something that you don't want to do. So thinking ahead on the SteamOS/Linux project that I'm working on, effectively I'm building an AMD-only solution. I don't really have a name for this project, so I'm going to call it Fifth. I think for Fifth, I want a mix of various Forth-style concepts. And perhaps the best mix would be the best of both worlds. A fast, high-level interpreter that's intent for doing GPU code generation, where I need chipset portability at runtime, mixed with low-level sourceless words for the CPU side, for simple x86-64, where I don't need portability at this time. Since this is for Linux, we should think about what we can do on Linux that we might not be able to do on Windows today. We first start thinking about execution. The Linux x86-64 ABI, when you're running without address space randomization, the execution starts at a fixed 4 megabytes in, and you can still do this today if you compile without FPIE. Also note, even if you did get position-independent execution, you could effectively just map where you want your fixed position to be, and then just start execution there and just ignore the original mapping that they threw you at. Another thing we can do is we can use page maps, and if we look at Steam Deck, we'll notice that dirty pages get written about as fast as every 30 seconds, which is an important number. It means it won't be overwriting too fast. So let's look at something we can do on Linux that we're not allowed to do on Windows anymore: the self-modifying binary. The idea here is that we have a cart file. The cart file represents the ROM. Actually, in this case, it's a RAM because we're going to be modifying it. So first we would execute the cart file. And when the cart file runs, it would realize that it's not a .back. And then it would copy itself to a backup file, cart.back. And then it would launch cart.back and then exit. This cart.back would realize that it is the backup file. And then it would map the original file, cart, at say 6 megabytes in. And it would provide that mapping and read, write, and execute. And then afterwards, it would map an adjustable zero fill. And that would be for when we're doing compilation or when we have data that we don't want to be backed up all the time. And after that, it would jump to the interpreter. And so if we look at the memory mapping, we'd have at 4 megabytes, we would have, say, a 4 kilobyte bootloader section. And then we would have somewhere, say, at 6 megabytes, we'd have the whole file. And then after that, we would have the zero fill. And the nice thing about this is we automatically create a backup. We don't have to write any code to save the file because it's going to autosave every 30 seconds. Also, the data and code is together, and we can make a new version just by copying the file itself. Inside the binary, we'd have a specific spot for the size of the file and the size of the zero fill. So the process of doing this execution, we can resize when we build the cart.back file very easily. So for source code, I'm thinking 32-bit words. For words, they're going to be direct addresses into the binary, and the binary is going to be the dictionary. Makes it quite fast to interpret. The nice thing here is they can be direct addresses because we fix the position. We're not using address space randomization. We'll just fix RSI to the interpreter source position, and then all the words will contain the next of the interpreter, meaning all the words end in the interpreter itself, or fold the interpreter in whatever form they want into their own execution. And by doing this, we enable lots of branch predictor slots because each of these end-of-word interpreters are going to be different branch predictors. So we can actually get this down into 5 bytes if we want to. We can use the LODS to basically load a word from RSI and then advance RSI, and we can use 2 bytes to look up the value in the dictionary, and we can use 2 bytes later to jump to the address for the next thing to run. So now we've gotten down to a 5-byte interpreter. Another thing I think I would do for variation is I would make source more freeform, not strict reverse post notation. In other words, with regular reverse post notation, you're going to have words that are going to push values onto a stack, and therefore your granularity is at the word level. If instead we have arguments, we can fetch a bunch of values off the stack right off the bat, and we can look them up in the dictionary in parallel. And now our branch granularity is dropping significantly, maybe say a factor of maybe 2 or 4, depending on what our common argument count is. I think this is a better compromise for when you're doing lots of code generation, which is what we'll be doing on the CPU, mostly GPU code generation. So for the editor, I'll just do an advanced 32-bit hex editor. I'll split the source into blocks, and then each one of those blocks will be split into subblocks. And the subblock will be source and then some annotation blocks. And so for every source 32-bit source word, I'm going to have say, 64-bit of annotation information split across two 32-bit words. And that'll give me 8 characters. Each of those characters will be 7-bit. And I'll have an 8-bit tag for editor. And the tag will give me the format of the 32-bit value in memory and give me whatever else I want in there. So I can adapt, for whatever I feel like doing in the future. And I can make this pretty uniform because I'll mostly have numbers and then I'll have direct addresses to words inside this. So that's it for now. This is a late welcome to 2026. I used the holiday for some deep thinking, but I think it's time now for some more building. Take care.